I'm gonna talk about some application of Schubert calculus to classical algebraic geometry. And let me begin with the definition of Prym varieties with some notations. So here, our field is algebraically closed field, and C is a smooth curve with a genus G, and pi is a double cover, which is flat and unramified. So flat means the fibers are equidimensional, and unramified means if you have a double cover, this is your double cover, then this point is unramified point. So our double cover has unramified means the fibers are just two disjoint union of this one. And J of C is a Jacobian, the set of line bundles of degree D modulo some equivalence relation. And tau is an involution. So if you have a double cover, then the involution sends one point of the one sheet to another point of the double cover. So it exchanges the point on the double cover. And given these notations, we can define a Prym variety as the connected component of the corner of this map. And if we consider the known map sending the divisor on the double cover to the divisor on the curve, then the inverse image of the canonical divisor gives you two disjointed connected Prym varieties. And this P plus, we can denote these disjointed Prym varieties, P plus and P minus, where P plus satisfies the dimension of the global section of the line bundle as even number. And similarly, P minus has a dimension of the global section as odd. So either one of these Prym variety, P plus or P minus, we can define Brill-Noether loci using some one-dimension condition on the global section of the line bundle on the double cover. So this Brill-Noether loci parameterized by the R here. So if R is odd, then by the definition, these all Brill-Noether loci are contained in P plus, and if we take even R, then these loci are in the P minus. And the Cochini and Breguet interpret this Brill-Noether loci in terms of some Schubert variety or degeneration loci in type D with just a one dimension condition. So what they did, they choose the Brancaire line bundle on the product space of the Picard group of degree 2G minus 2 minus times the double cover. So the Brancaire line bundle means it is trivial on the Picard group of degree 2G minus 2. And if we just pick a divisor of degree D with a sufficiently large n, then we can construct the vector bundle of rank 2n with this line bundle, the Brancaire line bundle associated to the divisor d tilde, like this one. And then they show that this vector bundle of rank 2n has non-degenerate quadratic form. And moreover, if we set the U vector bundle and W vector bundle given by like this pushboard of the projection, first projection of the line bundle associated to the divisor, then these two vector bundle has a length n, and it also turns out that these two vector bundles become the maximal isotropic subbundle with respect to this quadratic form. So isotropic means this vector bundle vanishes on this form, and the maximal means the rank of this vector bundle W and U has just a half of the original ambient space of the vector bundle of rank 2n. So they give us very specific quadratic form given by some residue functions. So given this form, that the vector bundle U and W becomes isotropic, and also the global section of the line bundle becomes the intersection of two vector spaces over the some point in the Prym varieties. So the Brill-Noether loci in the Prym variety becomes the Schubert variety with just a one-dimension condition on the intersection of two maximal isotropic subbundle like this one, yeah. And we can, in this talk, we can generalize the idea of the Cochini and Fregat in with vanishing sequence. So writers define the vanishing sequence as some strictly increasing sequence with a vanishing condition on the dimension of the global section of the line bundle associated to this sequence. And using this vanishing sequence, we can also define the pointed Brill-Noether loci with these inequalities inside of Prym variety. And as before, we can convert this pointed Brill-Noether loci into some Schubert variety or degeneration loci in type D inside of some orthogonal Grassmannians. So here, as before, we can set U as the maximal isotropic subbundle using the same vector bundle of rank n like this. And if we set Wi as a pushboard of the projection of the line bundle associated to the degree n divisor with some sequence, the vanishing sequence like this, then the vector bundle of this Wi has a rank n minus ai. So given this setup, we can make the some isotropic flag inside of the maximal isotropic subbundle, and then the dimension condition on the pointed Brill-Noether loci becomes the intersection of the maximal isotropic subbundle with isotropic flag, like this one. So we use this conversion from the pointed Brill-Noether loci to the Schubert variety or degeneration loci in type D orthogonal Grassmannian version to find the Euler characteristic of that variety. And as we have learned earlier, the Euler characteristic is the alternating sum of the dimension of ith cohomology group. And our plan is to use the connected K-theory and the Hertzsprung-Riemann rock. So the connected K-theory just connects the Chow homology with a Grothendieck group of covariance shape. So if we just specialize beta equals 0, then we can recover the Chow homology. And if we specialize beta equals -1, then we can get the Grothendieck group of a covariance shape. And we also apply this Hertzsprung-Riemann rock, where this in our situation the total class is just a trivial, so we don't need to worry about this part to compute this Euler characteristic of the pointed Brill-Noether loci. So to compute this Euler characteristic, we apply the existing formula in connected K-theory. So let me define some notations to state the formula in the connected K-theory for the orthogonal Grassmannian Schubert varieties, or degeneracy loci in type D. So here, this is a general theory. So V is rank 2n vector bundle with a quadratic form, and OG means the orthogonal Grassmannians, and the orthogonal Grassmannians has two disjointed connected components depending on the parity, and the degeneracy loci, or the orthogonal Grassmannian Schubert variety in type D, is given by the dimension condition on the intersection of this maximal isotropic subbundle with the isotropic flag like this one. So Anderson provided this connected K-theory class of the orthogonal Grassmannian Schubert variety as Pfaffian of the skew symmetric matrix associated to the certain partition lambda. So in our pointed Prym variety case, the lambda is the vanishing sequence. And here, the skew symmetric matrix is the diagonal part is all 0. And the lower triangular matrix part is just a negative over upper triangular matrix part. And we just assume that the length of this partition is even. And if it is odd, we can modify a little bit for this skew symmetric matrix to have some even size of matrix. And the entry of this skew symmetric matrix is given by these equations involving some raising operators. It is really complicated, so I'm not going to explain this part. But it involves some Chang class and the Euler classes. These are all associated to the vector bundle we saw earlier in the slide. And the Pfaffian is just the square root of the determinant of this skew symmetric matrix. So for example, if you have a skew symmetric matrix 0, x1 to negative x1 to 0, then the determinant of this matrix is just x1 squared. So if you take the square root of it, then you get this Pfaffian. Similarly, if you have a 4x4 skew symmetric matrix like this, then the Pfaffian of this skew symmetric matrix is given by this formula. So because the Anderson's formula is the class for the formula is for the class of the connected K homology class, so we can and the orthogonal Grassmannian Schubert variety is exactly the same as the appointed Brill-Noether loci in Prym varieties. So we can directly apply his formula to our situation. So and then by the nature of the connected K theory, if we specialize beta equals -1, then we can get the isomorphic class of the structure shift of this pointed Prym Brill-Noether loci. And if we set beta equals to 0, then we can get this Pfaffian formula. And if you compute this Pfaffian with the specific, the explicit skew symmetry matrix involving some Chang class and Euler class, then you can get the Schur P function. And we can further specialize these Chang classes of the maximal isotropic subbundle and the isotropic flag as some theta divisors to the j over j factorial. So here, theta divisor is just a zero set of Riemann-Zeta functions. The theory is really deep, so I'm not gonna explain what a Riemann-Zeta function, but it is just a zero set of that kind of function. So in the numerical equivalence sense, these are isomorphic. So we use these specializations to compute the class of the pointed loci inside of numerical group or the singular cohomology of the Prym variety. And then we can use the definition of the Herbert-Riemann rock. So we can, and we also specialize beta equals -1, and by the Chern character isomorphism, then this character of the K theory class of the pointed loci becomes exactly the this equation. It is quite complicated. And then for the next step, we can further generalize this pointed loci with two vanishing sequences. So as you see earlier, the one vanishing sequence corresponds to just the flag, isotropic flag of the vector bundle. So the two vanishing sequences implies the two isotropic flags. So we can interpret these two pointed loci in terms of some dimension conditions, the Schubert conditions like this one, and under some certain assumption, then we can convert this two pointed loci into vectorially degeneracy loci in type D, or the vectorially Schubert variety in type D case. And similarly, we can further ask the Euler characteristic of this two pointed loci, or just a numerical class of Prym loci with these two special vanishing points. Yeah, this is my last slide. So thank you for listening.